just start the session around 3-5 when everyone can join. I will start the session in 2 minutes. Setting up. Hello everyone. So this is Annu from IIT Hyderabad, and as a schedule, I have to take one live session per week. So every week I'm taking Saturday 3 to 5 days. So my email ID also, since new people join, I want you to mail me if you have any doubts. So basically, these live sessions are meant to be as interactive as possible, and so we are here to discuss the doubts and the possible solutions, how to solve the problems, so that it will be easy for you to solve during your exam. So the topic for week 3 was quite interesting, and the topic was cellular system design, capacity, handoff, and outage. So basically, for this course, there are two TAs. One Swati from IIC Bangalore, she takes uh, the last year question papers and all. So my intention is also to build some concepts and at the same time uh, to give you a different intuition, or so that's why I have prepared some of the simulation to show you what are the different capacity hand outage algorithms and the fading and the Q function that will help. So basically, the first topic is cellular system design, then capacity, then handoff and mobility, which is also having theory and resource reservation, classification of signal variation that will have this path loss, shadowing, and multipath. So far, we have discussed that wireless communication is prone to multipath as well as shadowing as well as path loss. For path loss, last week we have solved several questions. I think there will be definitely two questions that will be coming in your exam from path loss, that is free space path loss formula. And also you should know the receiver sensitivity. PR is definitely, it is a receive power if it is giving in a dB watt, or sometimes it is dB milliwatt. So the receive power sensitivity problems were there, and the noise floor was the one of the topics. So noise floor is actually multiplied with the noise power. So in that case, it will give the total noise power. So that the two questions will come that you can definitely solve easily using that formula. And then there are scaling models, and here I will talk about some simulation also, the Rayleigh, Bayesian outage, Doppler coherence, some worked problems with step-by-step solutions I will tell you. So these are the little bit different material in addition to what Sir taught in the class. So the question is like why cellular? So the reuse of multiple or the limited radio spectrum over space, which will lead to increasing system capacities. That's why we are going to cellular, and that's why one of the shape that we follow is hexagonal shape. And there is one formula for capacity reuse factor, that is Q is equals to root over 3n. So that is also one of the things that make ask the question. So it will provide the coverage with acceptable quality through base station placement. Also, the key parameters are like cell radius, the frequency reuse cluster size, that is n, and the reuse distance dr, and the intersite distance d. It is also having the path loss exponent alpha and the noise interference environment. So here, the hexagonal model and the reuse index n states that the hexagon based reuse index, which is n, is equals to I square plus ij plus j square, where ij is any integer greater than or equal to 0. And geometric derivation states that for integer ij, the vector from cell, if you have calling as a vector, so suppose this is a cell and this is any user. This is called one vector. Cell to a core channel or any channel is actually what it will be. It is, suppose it is having A1 and A2. So B is equals to A1 I cap plus A2 J cap, where A1 and A2 are the hexagonal lattice vectors, the distance between centers. So here also there will be some right? Distance between the centers is dr, which is equals to r root over 3 n. So here r is defined cell radius, and n is also defined as cluster size, which is also an integer. So for example, if you want to know how it got derived, you can refer some textbook. But what I feel is it's not required. You can just remember some of the terms. And mathematics also we can derive. That is not a problem. For example, ij is 1 1, or n, which is leading to n is equals to 3. So in that case, dr is equals to root over r n. So this is equals to 3r. So what it is saying, telling is like distance between two centers is equals to 3 times of the radius of cell. So cell radius, if you say, what do you mean by cell? So a base station has to cover a certain distance, and that will create one cell. The area that it creates, and it is having a radius. The cell is always circular in nature. Because area we are saying this is a base station, it will cover some area. So so this is the radius. If we talk about co-channel interference and SIR approximation, so assume only a first star interference, like suppose you are having only 6 neighbors at distance dr, the path loss is directly proportional to d power minus alpha, that we know. Okay. And alpha is the path loss coefficient. So for equal transmit power, so we are having this power formula, like if we are at 0, then it is equals to r power minus alpha, and alpha is like 0, so here it is 1. Summation of k, because here we are having k interface, dr of at distance k. So this is leading to dr, and it is minus power alpha, and here it is 6 by 6, because here 6 times it will be adding, so it is equivalent to 6 time multiplication. And this, what does this mean is like you can have, so here path receive power, so it is equals to r power minus alpha. This is the formula given as per the standard, and it is equals to 6 times, because a PR of k at k interference is t power minus alpha. So into t power minus alpha, you need to solve this. So 1 by 6 t by r alpha, because here you are giving that, sorry, it is minus alpha. So you can write this 6 r by t plus alpha. So if we substitute our dr is equals to root over 3 and r, then you are getting this. And you can convert to from normal a linear scale to logarithm scale. You can convert using 10 log 10 SIR. I'm giving you one example. How can you solve this? Because this was one of the questions. So, for example, you're having r is equals to 1 kilometer, n is equals to 4. So, what is n here? You remember this is n, the exact definition I'm telling, which is a cluster size. Okay. So, the cluster size and the path loss coefficient is 3.5. Compute the SIR. How will you compute it in this case? So, you have to use this formula in case of total interference. So as we know, dr is equals to r power 3n, which is equals to 1. Actually, my camera is not working. Otherwise, I could have switched it to it. So some issue is there. So yes, if you keep in this formula the values, you will have this value. So the comment, basically, we don't go directly for this actual answer, or just what do you say, just for getting some marks. What we have to see is like you're having SIR is equals to 12. 8. It is in linear scale. And if you convert into logarithms, there will be different value. So what it is showing is like using more tires or more tires improves accuracy, but this gives a good engineering estimate. Like you are having more tires, like you're having the first tire interface. Okay. If you are having more tire interface, it will give more accuracy, but at the same time, it will have the more estimate. Accuracy is more estimate. So there are some trade-offs that I have written in the points, like decreasing R, that is the radius, that is adding the sites, increases the capacity. Okay, obviously you are having small cells, and you are increasing the capacity. Uh, and second is increasing the sectorization. So if you have more sectors, then this also create the sectors. Then it reduces the force and interference and increases the frequency reduced coefficient, because the frequency reduced coefficient is equals to R root over 3n. Okay. D by R is the frequency reduced coefficient. This is dr is equals to the reuse distance. It is a reuse distance, whereas D by R is equals to root over 3n frequency reuse coefficient. At the same time, if you increase the transmit power, it will increase the extend the coverage, but increase also it may increase the interference to neighbors. Obviously, if you increase the transmit power, it may go to interference also, and due to which the interference can cause more interference. Whereas cell splitting versus micro cells, pico cells used in hotspots. Okay, the second part of the lectures was like traffic, airlines, and the grade of service. The offered traffic, it's often represented as A is equals to lambda h, where the lambda is equals to like how many calls you are receiving at per second, where h is the average holding time. So if you are in the calls, so you are getting lambda calls per second, and h is the average holding time for how much time you're getting that. So blocking probability, which is also called a grade of service, it uses the lag B for loss systems like no Q. So this is one of the mathematics term, and that gives you this BCA is actually A power C divided by C factorial summation of C k is equals to 0 to C A power K to K factorial. The K is number of interferers. And C channels, there C's are the channels, and A is the offered traffic. So the interpretation is like the fraction of calls getting lost when the system resources equals to C channels and the offered traffic. This is the fraction of calls lost. So there's an integration definition or the derivation. I wanted to give you so to have the basic understanding, because it is actually the Poisson arrivals. And last class I told what is Poisson distribution. An exponential holding time, which is MMCC. The steady state probability of k busy servers is Pk is equals to a power k divided by k factorial. The summation of n is equals to c a power n by n factorial. So when blocking occurs, when k is equals to c, so in that case, this is the case. It's the probability of in C cell. So when total number of interference leads to total number of channels, then it is blocking probability PC. So there are some solutions, like there's a trunking sizing. So if you have offered traffic K, A is equals to 12 inlines per cell. So I'll let you know what is the exact definition of airline. You should know that also. Of the traffic intensity that represent the continuous use of one communication channel for 1 hour. So it is a unique topic. We should know this. Everyone should know. As a communication engineer, airline unit traffic intensity that represents the continuous of one communication channel for 1 hour. So basically, here it the inland here inland is used to measure the total load on a system, and basically it is dimensionless. So now you may ask, what is that? So A is actually the inland, this lambda into H. And A is actually the traffic intensity in inland. This is the unit. Lambda, what I told, is average, or you can say normal only, average fall arrival rate, and which is falls per hour. What I told for H, H is average fall holding time. For example, I can give you one example. If a channel is occupied for 30 minutes during an hour, so what did this mean? What will be the A value? It carries 30 minutes per hour. So 1 hour in how much? It is 0.5, right? So it carries 0.5 lines of traffic. Now the question arises, if 10 users, suppose each of them making a calls averaging 6 minutes an hour, so total traffic will be how much? 0.5. It should be how much? 10 into, because here 10 users are there. So how many users? Lambda average call per hour. So it is A into, sorry, lambda into H. So H is how 6 minutes. So A, if 10 users are using, so A is equals to lambda means 10 into 6 minutes per hour. 6 by 60 will be 1. So 1 line. Whereas airlines are widely used in, suppose it is B and C. So it is different formulas to dimensionless telecommunication systems, which ensures target grade of service, which is made by, suppose, number of channels required to handle the expected load cost. So A, I think you understand. And due to that, the steady state probability of K busy servers is given by this. A, you should know. That's why I went deep into this. A is what? So it's a trunking sizing is one of the example. Suppose you have offered traffic is 12, A is equals to 12 lambs per cell. The target blocking is 0.001. And find the minimum C. How will you see? Fine. So first of all, you have to compute VC of 12, because here we saw this, right? This is a line B for loss of the system. So blocking probability. So this is the fraction of loss, or you can say blocking probability, which is probability. Probability is also not it's a fraction of call loss. This term in terms of probability. This is BC. Okay. So you have to keep all the values of A and C here. And then simultaneously check. Suppose C is equal to 16. You are giving P is equal to 0.003. 0.015 for C is equal to 17, for C is equal to 18, 19. You're having C is equal to 19 to make B less than or equal to 0.01. That is the case. So explanation is what? Like trunking gain allows fewer channels per caller. So here you are having 0.01. So if you choose 19, so it is lowering the fewer channels. 19 is not much number of channels. But see, how can you have this offered traffic based on target blocking rate B? So we have to compute individually and then you have to check. Now the concept comes like blocking versus dropping. That is a guard channels. Suppose new calls arrive. And handoff arrival is AH. So if you have to reserve the G guard channels for the handoff, you call effective channels C minus G. It is leading to handoff C is only C channels because here the G guard channels are there. So handoff blocking, which is a drop, is equals to B of C. The handoff blocking probability is actually B C A H plus ongoing tariff load. So practical sizing uses traffic models and target drop probability. So we have cell as C is equals to 20 channels. A new call offered load with AN is equals to 10. Handoff offered load AH is equals to 2. So we desire handoff blocking as it
Madam,
is
can
less
you
than equals
explain?
to. Yeah, can you please
Excuse me,
repeat?
madam. Madam, can you explain how to find C in example 2? Hello, madam.
Yes. Please tell.
And can you explain how to find C uh, in the above example?
Yes, sure. The point is, uh, in above example, they are asking you have to find the C, find the minimal C, like the C which leads to less than or equals to this target rate. So we have B as per the formula. So B is the probability for the blocking probability that is leading to grade of service. So according to this, A power C is equals to C divided by C factorial divided by summation of K is equals to 0 to C AK divided by K factorial. So since we don't know C, so we will try another. So we'll keep some C values and A we already know. A we already know 12 in lines. So C, suppose C is equal to 16, 17, or you may start from 1, 2, and wherever we'll check the B value. And wherever the B value is less than or equals to 0.01, we'll see that is a minimum C required. So that way we have to try because this is the formula, and in the formula we have to keep the values. So if you say formula is this BCA, this is the formula.
So, ma'am, it's a kind of hit and trial method.
Yes. Or since this formula is like is a geometric formula, you cannot uh, directly get the closed form values. C A power K factorial. So you have to keep in the calculator C is equals to 1, 2, and check the target P. The target P is if suppose the value is more, then you have to discard that value. Similarly, you have to check the values because it is leading to this value. On C is equals to 20, definitely it may lead to B greater than 0.01. The minimum C is this. That's it.
Okay, ma'am. Thank you.
Yes. Suppose we are having guard channel dimensioning. Suppose C is equals to 20 channels. And you call offered load AN is equals to 10. And handoff offered load AH is equals to 2. We desire handoff blocking, which is less than equals to 0.01. Choose the guard channel G. So in that case, we have to compute a new blocking with C minus G this way. And that is the handoff block probability is B CAH plus ongoing carried load. So we have to calculate with C minus G channels and handoff blocking probability with C channels considering total load. And we have to just try and check with G is equals to 2. And new capacity uses 18 channels for AN is equals to 10. Blocking the handoff uses all the channels with effective additional load. So 2. So basically keeping all the values here and checking the B value, and it should be less than equals to D, just less than. And if it is less than, then it is 2. Again, choosing the same value and getting a detailed numerical calculation can be done to A and B required for extra value. So this is the formula obtained from A and B that is important. This is the formula. So handoff mechanic is hard versus soft. There are two types. So hard handoff is like we have to break before we make a new connection, which is very common in GSM. It requires quick resource allocation to our job. Soft handoff is like make before break, which is used in CDMA where multiple base stations serve users, combine signals for diversity gain, and mobile, as the name suggests, like hard, it is hard, so it will break before a new connection. And you should know where that hard handoff is used in GSM as a general knowledge, whereas soft handoff is used in CDMA, which is 3G. And soft handoffs are just check in 5G which handoff is used and why it is used. That question should come in your mind. Which handoff is used with 5G and why? 5G uses make before handoff, that is, which is also called soft handoff, or dual connectivity in 5G via mechanisms such as XN based or N2 based handoff. This approach allows the user to maintain uh, the connection with the serving cell while establishing a connection with the target cell. Like we have to maintain at the same time. Because since the 5G requires high data rate, at the same time the connection proper connection. So in that case, it is required. Yeah, so the reasons is like ultra reliable, low latency. 5G supports critical services like autonomous driving, remote surgery. So that's why multi-rad internetworking also, like 5G often operates with LTE in non-standard mode, requiring smooth mobility across radio access service. And also, since we have a higher frequency range, we are going towards a high frequency range. It requires susceptibility to blockage. Mean handovers are very frequent. And so this handoff method reduces the drop cost, preserves the ongoing data sessions, and supports seamless mobility and heterogeneous. So you should know they may ask that. Can you just take 2 minutes break before starting next? Okay, so handoff rate and dual time derivation. They are suppose you are having user moves with speed v and cells are approximately circles with radius r. The average time spent in a cell for random direction motion is TD is equals to mean chord length because this is the diameter, and if you are any distance you're taking, then it is called chord. And the users can be anywhere in a cell. So this equals to the average time spent. It is equals to mean coordinate divided by v. Simple. It is equal to 2r divided by pi v. It's not equal to 2r. Actually, it is the mean coordinate is actually 2r divided by pi. And since v is v, so v is there. The reason is mean chord length of a circle for uniformly distributed direction is this. The handoff rate, which is lambda h, is equals to 1 by v, is equals to pi v divided by 2r. Basically, you should remember these formulas. You can ignore the maths behind it, like why this value is coming, but at least you should remember the formulas. And also this probability of handoff, like this is the since it is a exponential distribution. So we know that the exponential distribution is having the probability density function of 1 minus e power minus lambda, right? So the lambda is, sorry, h by lambda, h lambda. So lambda, this is the h lambda because the time also matters. You remember the probability is was ht, okay? And here the t is the holding time, so it is h. And since the lambda is equals to 1 by td, so this is coming 1 minus e power minus. Since it is an exponential distribution with mean h and the probability of the ball requires at least one handoff, it is equals to that. The number of cells, the derivation is number of cells crossings. So with rate is Poisson. And the Poisson is also one of the exponential distribution. The probability zero crossing in time t is e power minus h by lambda because it is crossing. So if you do 1 minus p of handoff, so 1 minus e power minus h by td is equals to e power minus h by td. Now, this is very, very important and very interesting. If you talk about this classification of signal variation. So I even have done some simulation for you. So this is a large scale fading and some small scale fading. So path loss, which is a deterministic power law, and the log normal shadowing, which is a slow variation of the hundreds of meters. So the rapid fluctuations due to multiple the multipath interfering, which is a wavelength scale, design must consider both path loss sets, baseline link budget, shadowing sets, location independent margins, and multipath sets, fading margins, and equalization needs. So there are two types. So if you are having some deterministic power law, then it is a path loss, and the log normal shading, which is a low variations or the very small interference from the obstacles, from stones, then it is called shadowing. But again, if it can determine properly, then it is called large scale fading. But in the small scale fading, it is a rapid fluctuation due to multipath interference, which is very very at the distance of small, which is lambda, that is in the terms of lambda scale or the wavelength scale. So in path loss model, we have free space and a power law. The free space path loss is P of Fs is definitely this is 20 log 10 4 pi t by 4 lambda. You remember that was a path loss coefficient. You remember PR is equals to PT, GT, GR, lambda by 4 pi square was there, right? So if you remember, we converted into dV. So this was in dV, dV, PT in dV plus GT in dV plus GR in dV plus this 20 log is there. So that's why term 10 log is there because if you want to convert X to dV, then it is 10 log 10 of X. But if the square is required, then it is 20. So that's why it is 2 here. So we can convert directly into dV, but it is 20 log 10 lambda by 4 pi r or d distance. So this term is the free space path loss. dB. And general power law is nothing but if you are getting the power at d distance in the dB is equals to power at getting the distance d naught. Suppose you are having the path loss at distance d naught already available. How will you calculate if you have a different distance? Distance is d naught, path loss you know, PR of d. But what is the distance at path loss of d? Is d naught. What will you have d? So with this, you cannot calculate at the same time from the very beginning. So with respect to this, what will the value? So it is nothing but simply minus 10 alpha log 10 d by d naught. You should know this formula by heart. This is important for sure, but this is also important. It will be asked very frequently in exams. Then where d naught is in the far field and fit alpha to measurements. It is alpha is the path loss coefficients. So it is getting the path loss is basically uh, subtracting this value. And what do you mean by negative here? What do you mean by negative here? Negative means in the linear scale, PR of D is equals to PR of D naught divided by D by D. Like it is getting scaled by 1 upon D by D naught. And if we talk about the shadowing, which is a log normal model, so basically in fx of x, if the x is the Gaussian random variable, then we know that root over 2 pi sigma square, v for minus x minus mu by 2 sigma square. We know that, okay? So this is the Gaussian model at mu and sigma, mu mean and the sigma as the variance, not variance, what is that? Variance is sigma square. Sigma, some other word is there. Variance is sigma square. Okay. So, sorry, standard deviation. This is standard deviation. Mu. So, what does this mean? Basically, if you are having this is mu. And what is a deviation in post from centered from the left hand side? This is sigma. So the receive power in TV with shadowing is nothing but that extra term will be there because this is we are telling this x of sigma. It's nothing but zero mean of sigma square dV. So this is the term which is getting added. Okay, the shadowing is basically spatially correlated. Correlation distance DQR is often tends to hundreds of meters, and this affects smoothing of measurements using handoff. Now, what if you are having the outage probability under log norm distribution? So outage means the probability of distance which is less than somewhat the probability of getting the received signal. So if the probability of getting the received signal is PTH, okay, and if it is less, that means outage is there, like some we are not able to receive the signal, then it is will be given by a distance R. It will should be less than PTH, right? So what is the probability of this? That you call is an outage probability. And since we are already having this formula, so what will be this? The P out of D, P out of D is equals to probability when the probability at distance T in dB is less than the minimum received signal probability, then it is equals to Q of mu PRD minus PTH divided by sigma dB, where Q is nothing but the Gaussian tail. So Q we know since we are having suppose this. So tail probability is the Q. So suppose this is X. So what is the probability of X is nothing but probability of X is greater than X naught, and this is X naught. Q of X naught is equals to probability of X greater than X naught. What is the tail probability here? Gaussian tail. Okay, this is the Gaussian tail. Right? This is yeah. So this is one of the example. You can keep these values here, this formula. So because we know outage probability with the log normal distribution are scheduling and the last scale fading, you're having is equals to Q of mu PRD minus P3 is divided by sigma dV, where mu PRD is nothing but is the mu PRD at distance t. This formula is from here. And this value is PR of D of naught dV minus 10 alpha log 10 d by d naught. The formula that is given. And if you compute a distance d, you have to keep all these values first in this formula. Once you get this value, this formula, then this formula, this formula, these values are already given. And Q of that value you have to get, and you will get this one. So interpretation is very small outage at this threshold in the parameters. Because what is the threshold? The probability is less than this. Also, Q function is decreasing in weight. Now we have talked about large scale fading and shedding. The other term comes as small scale fading. So in small scale fading, the Rayleigh fading is one of the fading technique. So it is having many scattered components, no dominant line of sight. Duration fading is dominant line of sight plus scattered components. So that is it. K factor is equal to ratio of line of sight power to scattered power. The statistical description is envelope PDF, power PDF, and SNR distribution. So if we have to envelop R PDF for label, so this is the PDF distribution function for that. And if the probability density function at distance R and the Rayleigh fading is considered, it is nothing but R divided by sigma square e power minus R square divided by 2 sigma square, where R is greater than or equal to 3. So you remember that Rayleigh fading is also one of the exponential uh, model. But how it looks, you should know how Rayleigh fading looks. I'm sharing my screen. Uh, so I did not plot it this Rayleigh fading. So there's some log normal shadowing. So if you have outage probability and if its distance is increasing, so obviously the distance is increasing, the outage probability will also increase. But how it increases, like it will be almost 0, 0, 0, then it follows the positive exponential curve. Exponentially, it will reach. At some point of time, it will be very high. And this is a shadowing plus relay. This is also one of the since the shadowing is added, so it is Gaussian because whenever you add something Gaussian, it will become added Gaussian. This is the PPSK modulation. Not like this. Really fading looks different. Yes, I wanted to show this. This is the distribution. So you can see here, the Rayleigh fading is defined by sigma, obviously, but how it is increasing? Suppose you are having, first of all, it is defined for only x greater than equal to 0. So here we have defined r divided by sigma square e power minus r square divided by 2 sigma square. What was the formula? R divided by sigma square e power minus r square divided by 2 sigma square. In the exponential also, you had that formula. Remember, in x power e power minus x square divided by 2 sigma square, right? But the additional term in Rayleigh fading is r divided by 2 sigma square is multiplied in front. So if we multiply the Gaussian function with this r divided by sigma square, when r is always greater than 0, then in that case, it is coming like this. And how sigma is determining here? Because the Gaussian term is multiplied by r. So it is directly scaling by r, but at the same time, it is scaling, descaling by 1 by sigma square. So if you have sigma 1, then it is more peak towards front side, initial part. And when you have sigma is equals to 2, then it is less peak, but at the same time, the intensity is reducing. Intensity is reducing, but the area, uh, what you have observed is like the area in both the color curves is same. And what is that area? It is 1 because this is the probability density function, and the area under the probability density function is always 1. So you should know and at least try to interpret it whenever you see the difference. It's difficult to remember some points. Yes, so the only term here is R given by sigma square. So you saw this is the sigma 1, sigma 2, sigma 2, sigma 1, sigma 2, sigma 3, where sigma 3 is greater than sigma 1 because it is here decreasing. So here decreasing volume. This is R. So here it is defined from here. So average power is omega is equals to 2 sigma square SNR gamma is exponential. So it is F y of y is equals to 1 by sigma gamma average into E bar minus gamma divided by gamma bar. And if the power of outage is calculated in Rayleigh model, then it is 1 minus E power minus T divided. So this is average SNR or threshold you can say. No average SNR. This is your outage threshold. Okay, so if you want to calculate PER, averaging over Rayleigh fading in case of BPSK, so instantaneous PER for BPSK and then AWGN at SNR gamma, then in that case, PB of gamma is nothing but just a second. Guess what happened? I'm taking class. Yeah, it will take total 5. So if we calculate the average BER over Rayleigh fading, then it is a standard result. We should know. What it shows is like if we have diversity, what do you mean by diversity? If we say the same signal over different antennas, that is called diversity. If we want to achieve the AWGN performance, which is less noisy, then in that case we have to use the diversity and the coding techniques. There are different type of fading. One of the fading is Rayleigh fading. So in that case, and you may ask when the Rayleigh fading is used, when the Rayleigh is used. The Rayleigh is used for non-lines. Rayleigh is used for lines. This is a PDF because now I would like to show you how Rayleigh fading looks like. The Rayleigh curve. So it is also similar, but it is also similar, but it is having several other parameters. So it is also like this. So here it is not defined by sigma only. It is defined by A different parameters or K, sorry. Here. So the K, when K tends to 0, it reduces to Rayleigh large K approximate AWG. So K here is square divided by sigma square, which is less to 0. What does this mean? It means that S is equals to 0. So if you keep S is equals to here 0, then it will be to Rayleigh. So next topic is Doppler spread at the coherence time. Like maximum Doppler when the uh, transmitter is moving, then at the same time there will be frequency shift that is called the Doppler frequency, and the moving velocity is the velocity v, and c is the speed of light, and what is the frequency? Which is this. So the FD is equal to v divided by c. That was an initial frequency, but Doppler frequency it became this. It is multiplied directly with v by c. The approximate coherence time. So what do you mean by coherence time? Suppose you're having a frequency, the message here. Then you convert it to the transmission, then it will be like this. So again, the time for which, or the bandwidth for which the channel is constant or almost constant, that is called coherence bandwidth. Okay, and which is directly proportional to 1 by RMS delay spread. Because if the delay spread is more, then again, the coherence bandwidth will be less. That was if the signal bandwidth is channel bandwidth is less than it, frequency is flat, otherwise it is frequency selective. Because suppose you are having a bandwidth of this, and the signal bandwidth is having this, then it is that this area will be caused by frequency selective fading. Okay, because the bandwidth is only this. If it is less than this, then it is simple flat. So it is called frequency flat. Otherwise, frequency selective fading will be there, and that requires equalizer or link budget we have already covered last time. And there are some steps like how to do the practice problem. So if you want to calculate SIR for hexagonal cells, including second tier interface, then for a given A, compute C. We are having threshold using L and B formula. Then compute the probability a call experience at least one handoff with BRH. Then compute the average BER for UPSK. how to approach a numerical problems, you have to write first you write what are the parameters given. Once you write what are the parameters given, then you will understand, okay, these are the parameters along with unit. Then if you understand with unit, hexagon lattice vectors, if we have this, uh, center spacing, choose integer pair to the output and distance squared between this. dr is equal to r root over 3n. As before, we will use this when summing interval tires. Interval sum, including multiple tires, then the SNR. We can compute B of 80 in 12 using recursion, using directly formula. Yeah, we can show using this. Keep me 5 minutes. Keep on charge. sharing my screen for the board. So this notebook, which I will share with you, demonstrates a basic simulation and visualization for week 3 topics like cellular geometry, SIR, airline B trunking, dart scanner channels, handoff statistics, log normal scheduling and outage, Monte Carlo simulations with relay fading, and a BER for BPSK overhailing. This contains a short explanation of each topic and also code shells that compute and plot results, ready to run examples and parameters that you can change for your exams. Suppose you are having utility functions that is used throughout this notebook. So these are some NumPy, maths, Skype special, import ERFC. This is one of the function. ERFC. This is how it looks like. Formula is this. Error function. Error function complementary. So this is 1 minus 2 by root by 0 to x e power minus t squared e squared. So because this ERFC, you can define Q as this, that's why ERFC is used. Then using the formula for SIR, signal to interference ratio, which is having alpha as parameter, R as parameter, the tire info as parameters, okay? So where the numerator will be alpha into minus alpha, R power minus alpha, right? Denominator, suppose it is initialized with 0, then for n and d is equals to r into max square root over 3 into n value. Denominator equals to plus if we are adding for the how many interfaces are there. Okay, and then Erlang B, simply the formula for B is equals to 1 for initializing that because it is multiplication. B is equals to A into B divided by A into B plus K. Then finding the minimum channels, again, using the same try and error for C is equals 0. Then if it is true, then C is greater than 0. Otherwise, it is will be added plus 1. Otherwise, it will run. Then we have to keep the target block. In our example, it was 0.01. Similarly, if we are having guard channels, which is steady state, C, G, lambda n, lambda h, then mu is equals to 1 by h. Lambdas we are keeping in the array. For k in this range 0 to c, it is if k is less than c minus g, then lambdas will be appended by lambda n plus lambda h. Otherwise, lambdas will be appended by lambda h. So this will goes on and it will keep this value. We can go through this. handoff probability uh, will be given by this. Outage knock novel will also return for the function. And if we have to define the area average outage, it's also written function. There's a non-correlative function. What it says that if you do the random experiments and if you repeat it for 1,000 number of times, then the distribution that will come out of that is a Gaussian in nature. So that uh, it shows that every random experiments, if you sum it and if you try it several times, and it is coming the Gaussian random distribution. So first we will compute hexagonal multi-tier example. If we keep this all values, compute approximate SIR assuming 3 4-channel tires. Suppose changing alpha or tire multiplicity to see the effects. So alpha is equals to 4. So what it is showing is like it is linearly dependent. And it is 3. Suppose I'm changing alpha 5, how it changes. Because right now it is 8.68, let's say 5. So if alpha is increasing, SIR is also increasing exponentially because it was if I'm decreasing alpha, it is decreasing. So as we know, elang B, which is a unit and is one of the way, is used for law system that is no Qs. So we'll compute the minimum channels required for target blocking probability. Suppose A is equal to 12, target 0.01, directly keeping in here what it shows. The minimum channels are 20. See how this distribution is. So for different C values, these are indices. Uh, you are having B of C of A, and till the point you are having 20, it is 0.09. Otherwise, if it is 21, uh, it is a minimum value that shows very close to 0.01. So that way it is 20. Space. Guard channels, we compute steady state probability and blocking prop metrics for simple guard channel policy. That cases, values are there. So, for example, C is equals 30, G is equals 3, mu call blocking is equals to 3.98. And the handoff drop is 2.17, 10 power minus 8. For different K values, PIK is calculated. So before we move to the handoff statistics, dual time and the probability or call experience at one handoff. So if we assume the random direction within a circular cell approximation, then what will the dual time? TD is equals to spot. So that is giving 12 times TD is equal to 76.39 seconds. And whereas the probability of where the cell has greater than one handoff is 0.9 C. If you are having this Doppler frequency or the delta time, then definitely you are having the probability which is greater than one handoff, and this is not required in the cellular system. So next is outage with long normal shadowing, which is analytic Q. So we have to compute the outage P out using Gaussian Q function and the area coverage. What it is showing here, at D is equals to 500 meter, the receive power is minus 60 dBm. The average area outage is 4.21 e power minus the 8. So the outage probability is obviously increasing with distance, and after some point in time, it is increasing exponentially. So let us do this Monte Carlo, because in Monte Carlo, after repeating several number of times, it is called Monte Carlo auto simulation. We will include the small scale fading in addition to large scale fading. This typically increases the outage compared to shadowing mode. So histogram of receive power. This is different and this is different. This is a histogram. And it is see, it is a receive power, and it is following the Gaussian, because we have performed how many times? This number of times. So Monte Carlo's experiments also say the same. If you perform experiments several number of times, then it's like that. So this is the analytic versus simulation. We are getting exact same for the PER in BPSK modulation. And how the Monte Carlo estimate for area of the outage converges as the number of samples increases fixed. The convergence area outage was like in 10 power 4, it was like this. If it is greater, it is here. And if it is more, you are having convergence area outage less. This for the lecture notes we covered. Yeah, so if we are having propagation exponent n, and if n is more, then PR is decreasing. So it is inversely proportional to n. So this is n1, n2, n3, and this is like propagation coefficient n. So there are frequency hopping parameters, like it will reduce the interference, and will have the intra-cell interference, adaptive capacity. These are the terms that we saw that is predicted. Alpha we saw, right? That is 10n. In Bluetooth, we are having 1600 hops per second, whereas GSM, we are having hops every per second. To see, online inline calculator can be found at this link. So consider the figure. From that above, determine which of the following given curves correspond to highest path loss coefficient. So since receive power should be this T, so which one you should say? Obviously N5, because it's the highest.
Complete this, the teacher gets a little confused. Then she asks him to make a boy thinks
N5? Madam, N5?
now that clock is also missing. Now the teacher finds this a little strange. She understands that the matter can be serious, so she advises the boy to see a doctor. But the boy ignores her advice. When he shows his drawing to other
Correct answer, madam.
one says,
N5 is the correct answer, but what is this sound?
that something is really wrong. He goes to the doctor with his twin brother. The doctor listens and then gives him a anger and says, draw a house on this. The boy tries his best when he is unable to draw.
I think it is coming from you, sir. Yes, yes. It's coming from you. The answer is N5. N5 because N5 is here the steepest one. As obviously the N increases, the path loss coefficient is decreasing. And this 11 nodes. So consider the following statement. Low RSSI and high SNR is unlikely scenario. Uh, yes, because this is both are directly proportional to each other. And high RSSI and low SNR implies a bad scenario. Both statements are true. Lecture number 11. C by I is equals to 1 by I naught D by R. For improving C by I, frequency hopping, interference suppression, it is antenna technique. C by I is increasing to guarantee. That's the same. Yes. What it's telling is suppose RSSI is high, which it chooses own base station. The receiver quality will be high, which is SNR. Channel will be good. Okay. But if the SNR is high, RSI is high, which is near own base station, close to own base station. Whereas receive quality is low. Suppose it is SINR is due to interference also. Whereas RSI just signal quality, whether it is correct, which is proper or not, it will be depending on that. Whereas if we are having low SINR as well as RSSI, which is edge of the cell or high interference, in that case, inter-cell handoff will be happening. Whether it is not good channel, good channel. Whereas this RSSI is low and SNIR high, it is not possible, it is unlikely. That's what it is telling. For a hexagonal symmetry, which is a valid cluster size, so it has to satisfy this I square plus J square plus IJ or some integers I and J. So if you keep I and J are some integer only. So if you keep 7, then I should be 2 and J. This is correct. So for n equals to 2, 12, what ij values is satisfy? Any ij it will work. So this is correct. So both are correct. Which of the following methods can be used to improve the carrier power to interference power in an interference limit scenario? All of the above, yeah, we saw sectorization, intracellular turnover, and frequency hop. This problem is about finding the path loss coefficient of a single breakpoint path loss model in a communication scenario. So you have distance and average receive power reading at different distances tabulated below. What is the difference between measured and the measured receive power in dB meter and estimated receive power at 400 meters? So we have to use this formula. Measures receive power and estimated. So this formula gives that the, the estimated receive power is a function of distance d after d break is given by this value. So it is minus 6n. So hence the difference between the measured and this received estimated power would be this one. So this is the received, this is estimated. Minus 15 plus 6n. For the problem above using least square method, estimate the path loss coefficient. So PI minus PI cap. Using simply this formula, measured is minus 15 from where they have taken minus 15. Okay, so they are kept in these values. This is the formula. And PR of 400, which is the break, which is equals to minus 6n. Okay. Uh, this, sorry, this is 0, they have kept it. This they have kept is 6n. So this is minus 6n. Measure an estimated power. But as per this tabulation, the estimated power at 400 is minus 15. So minus 15 minus the measured one and estimated is minus 6. So it is minus 15%. Okay, nice. So for the above problem using the least square method, estimate the path loss exponent. We have to estimate that. So objective function j of n with different values, p1, p2, p3. If we just do this differentiating with respect to n, and the n gives this value, which is the path loss coefficient. So consider the cellular system with hexagonal cells and a cluster size of 3. If 120-degree sectorization is employed in a system, how many tier 1 interferers will be present in worst case scenario? So with hexagonal cells, a cluster size of 3. We have cluster size of 3, hexagonal cell is there. How many tier 1 interferers will be present worst case scenario? So a 3-cell cluster cell system is given as above image. C naught is the cell of interest. C naught is a cell of interest. One, one, two, three. One, two, three. So a source of worst case SANR user at C, P. Okay, at P. Because it is cell edge. So P. C1, C2, C6 are the core channel cells. These are the core channels. So 120-degree sectorization in this line also we can see C3, C4, C5 contribute to core channel. C3, C4, C5 core channel. Just you have to calculate the distance. Consider user moving the constant velocity in open area. Assume the both transmitter and receiver are approximately the same height. Massive Doppler shift is when the user moves away from the base station. Uh, so away from the base station, obviously there will be path loss towards the base station along the lines of side. Yes, no matter wherever the user is moving, it is moving with this with the velocity. So in that case, it is line of sight, non line of sight. In the direction perpendicular to line of sight. Uh, so both A and B answer is. Doppler shift is maximum when the angle between the direction of movement and the user is 0 or 120 180 degree. The random variable x follows a log normal distribution such that the random variable y is equals to log f has 0 b. The mean of x will be. So if x is now log normal, then y is the normal random variable. Therefore, y is again 0 to 1. So expected value of just a second. So we have to calculate using this formula. It is given root over E. Software handoff is a procedure related to inter-sector handoff. So inter-sector handoff. Software handoff is intra and different discipline. Okay, so actually I have to go for my meeting. So today stop here. Thank you so much for joining part of today's Raksha Bandhan. Happy Raksha Bandhan to both of you. Thank you so much for joining.
Thank you, madam.
Thank you so much.
Yeah.
Okay.